right, let's talk about the future. We'll do that on the board because we'll do that as I think, okay? So what? Future of what? Future of additive or future of additive in medical? What do you think? What should we talk about? In general? Okay. So, future of AM, yeah? I've got a couple, I've actually got maybe a little bit. It's an old presentation, which I gave. Did anybody go to the Inside 3D Printing when I was presenting at, in Mumbai? No? Good, okay. All right, I'll show you the presentation I gave there. It was a couple of years ago, but I think it's still quite relevant to today and this kind of discussion. What is the future of additive? But let's just move along a little bit. Some of the things that are coming to my mind, what I'm seeing a lot of at the moment is what is really, okay, if I see AM, there's sort of like a bit of a divergence effect, in fact. And the way I might be able to say it, maybe even three ways. Industrial, research, business. From industrial, there's a lot of interest. What is industry looking at from additive manufacturing? So they have a number of requirements. Biggest one probably is quality assurance. So when I say industrial in this context, I'm saying people using additive manufacturing for making things, okay? So direct digital manufacturing, as we sometimes refer to it, certainly what Brent Stucker used to call it. So that might relate to things like consistency of build, ability to detect problems during or preferably before they happen, at least definitely detecting them as they happen, so that you can, the worst case is you can stop the process. But ideally what you want to do is actually detect it during the process and maybe change the process to compensate for it, which means prediction. So that is also a research tool, but I'm not really talking about industrial in terms of what we can do at the moment and what's possible, but it's also helping us to drive our research. So this is really, I suppose, you know, I'm also talking about research at this point. These are research directions, if you like. And I'll explain a little bit by what this means later. But certainly industrial, so they want predictive mechanisms. Okay. Imagine, okay, I showed you the example of the LEAP engine nozzle, right? That one is pretty well sorted, if you like, from the perspective of quality assurance, because they are not going to change the design. They're not going to change how it's built. They've basically worked out through a lot of trials and sequences, this is how we are going to do it. Right? So that process is pretty well fixed. What, however, if you had something like that, but it may be that you know, you're going to make modifications of the design through regularly. It's a customizable component. In that situation, you know, it's not fixed. Process is kind of fixed, but some of those customizable elements, no matter how small, may have sufficient impact on the build to cause it to fail. So that's what I'm meaning in this sense. So what would be ideal is if you had some kind of predictive mechanism during the design and build setup process to say, hang on a minute, there's a problem space here. So this might be using very good simulator software, or it might be using more black box approach like an AI, routine machine learning mechanisms. And some of this might be related to feedback from what's going on at the moment, and knowledge that we are gathering but not necessarily using in an intelligent way. So AI methods can be dealt with today. There's a lot of information. I mentioned that I'm doing this work with an aerospace company in the Netherlands, and the student students that's working on it, is doing his PhD, is looking at a machine learning algorithm to try and work on this. In the past, the problem was experimentation. You know, when you're doing research, how can you make sure that you're doing enough builds? He already has, before he even started his PhD, terabytes of information stored up on all the builds that the company had already carried out. And a lot of those are failures. So that's even better. He's got access to a lot of failed information on failed builds, and he's able to then exploit that and see if he can work out a mechanism which will help him to understand how those builds actually did fail, and whether we can implement an algorithm to prevent it happening in the future. Okay, so that's kind of what's going on here. Another thing that industrial kind of likes or wants is big parts. One of the problems that has prevented greater use of additive manufacturing is the size of the builds. Powder bed I mentioned, you know, if you are running a powder bed system in titanium, you've got this 500 by 500, it's hundreds of thousands of dollars of raw material. So that is difficult for companies to deal with, and the investment requirements and all of that. It's not just the machine, but also the consumable items. So ways in which to achieve big parts without significant cost implications. So one might say big parts versus cost as being a direction to go. How do we do low-cost additive manufacturing of viable materials with at an acceptable cost without compromising material properties and speeds and other things as well. So this is actually quite a significant problem. Obviously, companies want to do this all the time, and if you look at every machine that comes on the market is slightly cheaper than the previous one, which is great. You know, this is a good thing. The reason why they're slightly cheaper is because they are more confident in the market that there will be people prepared to pay for those machines. So it's an interesting sort of snowball type of effect that you know, confidence builds competitiveness and helps in bringing costs down and things like that. So this we can expect to happen, but it's going to, you know, there's also this other side of things of trying to make improvements as well. So these are the sort of drivers, I think, for industrial. What else? You know, the quality assurance aspect also covers things like reliability of the machine as well as the reliability of the process. So we don't want components to fail. We don't want downtime. We want easy training and ease of use of the machine as well. We want plug and play. So there's a lot of other aspects which revolve around that. But it's really about creating industrial scale technology. So they want big, they want good quality, and they want quality of, or predictability in the build. Research wants you know, adaptability is probably the best word. You notice I mentioned a couple of the machines yesterday in the bioprinting presentation, that there's a lot of machines, and you know, we want multiple channels. We want the ability to present. Oh, it's okay. Present the material in different ways, whether it's if it's a liquid or a solid, and we want those on the same machines. So the sort of extrusion-based technology actually works very well in this context because we can adapt it very well. And if we then also say, you know, for example, one of the groups that I was had some contacts with, they were looking at plasma treatment of the polymer extrusion process. By plasma treatment, you can turn a hydrophilic polymer into a hydrophobic polymer, and vice versa. So you can allow, and if you've got a, you know, something that helps to absorb fluid, in that's good from a scaffold's perspective because it can allow greater penetration of the cells. You can even encourage them to move into the scaffolds more effectively. So a lot of the issues around vascularity, etc., helping fluid flow. So adaptability. So having that on the machine itself, where you can extrude, where you can treat, surface treat, maybe even present the bio-inks all at the same time. That's an interesting sort of perspective on things. So adaptability is definitely one area. They're not worried about size as a rule. Size is a scalable thing in many research perspectives. A lot of variation in materials. Adaptability might also be variability, if you like. So I could say materials, but I think it's worthwhile mentioning materials separately. So additive, subtractive, additive formative. I used to used to play around with the term of creating what I called the time machine. This is very relevant in this sense. Totally integrated manufacturing environment. I had this vision of some kind of carousel system, not just carousels with the feed heads, but then carousels on the actual machine itself, where you can feed a part in a variety of different ways through a system, treat it in different ways, change the sequences, and come up with a lot of huge potential in variability. That machine, I can't remember the name of it now, that I showed yesterday, that's kind of part of my vision of a time machine. So materials and adaptability are great for research and cost. And you know, bringing the cost down, and one of the great things, as we mentioned, the reason why we are here today, that there are so many people that are excited by additive manufacturing, is because we can all see it and see that we have access to it. It's cost effective, it's low cost, we can use it. I can give it to a student and I'm not going to be too worried about whether that student breaks the machine or not, because it's not going to be a huge investment to fix it. In the old days, you know, you never have them. You don't replace, I'm sure you all had that experience, you know, okay, look but don't touch, you know, and you don't learn that way, yeah? You learn from experience, you learn from doing things. And me personally, I say you learn from making mistakes. You know, this is the disruptive side of me, you know, that the things that I learned most is when I did a bad job. And I don't want to ever be in that situation again. So I try my best to work at it. And that includes me being a lecturer, by the way. My first lectures, you would not have liked. Okay? You would have thought, oh my goodness, you know, this person is terrible lecturer. And so, and I knew it. And that's the other thing, is understanding and recognizing your mistakes as well, and recognizing your failings. So there's ways to deal with that. You either improve yourself, or you put yourself in an environment where it can be, you can get assistance from other places. So building your teams and things like that. I think the issue about this, and we talk about adaptability, is that this in the essence is multidisciplinary. Yeah, that it's very difficult to do research now, in my view, unless you are part of a multidisciplinary team. And it's not helpful. University structures are not helpful. Universities are structured a very hierarchical way: faculties, departments, labs. So how does a lab over here work with a lab over here when you have very little opportunity to talk to each other and learn what each other are doing? I encourage you to take control of that and go and meet with people and break down those barriers. It's up to you, really. You know, it's pretty clear that the system doesn't really help very much in doing that, in allowing you to build your multidisciplinary teams. So you have to take control of that yourself. Now, the great thing is that, and you know, some of the things that you can take advantage of, and this is partly why you have, I don't know, do you have fraternities here? You have houses or dorms where essentially you just have a group of people and they're not collected together under a discipline or a theme or a topic. They're just a bunch of people that just happen to be in the same place. And so, you know, in the US they call these fraternities, which are all sort of based around student dorms, student accommodation, where people just sort of, you know, happen to be living there, and you know, you find that your next door neighbor is a poet, and the one next door is a political scientist. And so having those kinds of conversations and building those kinds of relationships are partly what university life is about. And so, you know, you should also take advantage of that in your professional life as well. So, you know, that kind of thing, or you know, keeping touch with your school friends or whatever. But learning about the alternative perspective on the same problem. So biomedical engineering requires engineers and biochemists. You can combine them together so that they learn the same thing. That's fine, that's a good thing. But you know, you can only learn so much in a set period of time. So what happens to a biomedical engineer is that a lot of the real detail is missing from their from the education. To me, that's actually not a bad thing necessarily, provided you also have access to those people that do have that deep knowledge. So what we turn for, you're familiar with the T model? Okay, breadth and depth. Okay, so this is about knowledge. So this is the knowledge T model, if you like. So this is basically the idea that for perfect understanding of a problem, you've got to have the depth of knowledge, which is what most universities have focused on. But what is more difficult and what is happening more commonly today, but it's taking time, is the breadth model, which allows you to understand context and application and how it fits in other environments and in other disciplines. And these days, you know, we have, you know, mechatronics devices. You call them what you will. Even now, we talk about that in context of that's not even big enough, because you've got data and you've got management and you've got design. All of those things should feed in there as well. So you basically have a whole bunch of different disciplines which must combine in order to be successful. Okay. Anybody been involved in startups? A few. Excellent. How many people would say that they've been successful in startups? One, maybe. Maybe. Yeah. It's a hard process. It's a very exciting process, and it's a very rewarding process, because you learn an awful lot outside of your own discipline, yes? And if you don't, that's why you fail, to be honest. You know, because a great idea is only the starting point. Even a great product is only the starting point. How many great products have actually failed? Many, many, many. Okay? I've got a good example of that. And that's probably relating to what I've got here. And rather than put it up on this thing, and now the projector's shut down. So can we start the projector up again? And my computer's shut down as well. I'm going to have a strong word with Michael Dell when I see him next time. Just bear with me. Any questions while we're going at this point? Amazing. I think you guys have started to exhaust your questions. Finally. I have to compliment you all, by the way, for the amount of participation in this workshop. Oh, I need sound. I think that's going to work. Let me check. That's probably because it's here. No, that's here, isn't it? Why is not sound? Oh, volume? No, it's definitely not coming through. Do I need the other thing? There was... Ah. Yeah. That's probably in it. We're okay now, yeah. I'll try that. Yeah, excellent. Good. Right. So let's play this. Autodesk. We'll have a Zen moment. It's cool, this, isn't it? Are any of you familiar with the Autodesk PR9 project? So Autodesk have this location in California. It's called PR9, and it's really sort of like a bit of an incubator innovation center. And some of it's a very interesting work, and you're probably familiar with the old zoetropes. These are trying to create moving images by just rotating them. This is a 3D zoetrope. So this is actually an object that appears to be moving because it's rotating. And it's beautiful. I think some of the parts that have come off this, absolutely excellent. So the idea behind this is to try and sort of, I guess, encourage you to think outside of the box a little bit in terms of solutions that you might like to consider in your research. And this presentation is based around the concept of disruption. Anybody familiar with this guy? Anybody think of his name? No? Probably. Any high jumping specialists in India in the Olympic Games? This guy's name is Dick Fosbury, and he's an American, and he was a college student, and he lived in a small dorm when he was at college, and he had the top bunk. He shared the room with another guy, and he had the top bunk, and He was a bit of an athlete, and he used to work. He worked out this method of getting into the bunk. You know, you had the door open. He'd go into the door and spin round and land on the top of the bunk. Okay, on the bed. And he kind of thought, hey, hang on a minute. This is actually quite a cool way to do the high jump, because before this guy, everybody did what was called the Western roll, where you faced the bar and you put your front leg and you tried to roll over the bar. And that essentially was a limitation on how high you could jump. And this guy then worked out a method to jump higher, won a gold medal. And now everybody jumps this way, and all the highest jumpers have to be. So he was an innovator. He was the first person to do this, and he's a great example of what we call a disruptor. So Dick Fosbury, basically what I would consider to be a prime example of a disruptor. And you think about this from the perspective of business. People, you know, what is it? There's a couple of examples. It's about success in business. There may even been people that tried to do this but maybe didn't have the skill that Dick had, or the stature or the athleticism. But he was the one that everybody now refers to, the Fosbury flop. That's the method of jumping. So he was a radical changer, applied innovative thinking. Who's that guy? Fantastic. People know him, even though he's been dead for a few years now. Obviously, one of the people that we associate with innovation, correct? But none of the technology that Apple produced was truly innovative from a technological perspective. It was the packaging, the presentation, the fact that you had an astute businessman, because that's what Steve Jobs was. He wasn't really a technical geek, because you had Steve Wozniak, amongst others, and Johnny Ives and other people that were supporting the Apple technology and developing those key cool ideas. But he was definitely a visionary. He implemented or allowed the implementation of technology before it was potentially successful. Things like the touchpad. I mean, people do that, but he managed to package it up correctly. Personal computers, a lot of, the iWatch, various things which other companies did as well, and sometimes did in a better way. But for some reason or other, the packaging and how it was presented by Apple was better and more significant. So he's definitely one of our most well-known innovators of the modern generation. Any idea who this guy is? Okay, I'd be very impressed if anybody knew who this guy was. Particularly if you're not Australian. He's actually an Australian. His name is Silverbrook. And even now you probably don't know why I'm presenting him to you. He is, however, he's an Australian inventor. He has, to his name, 4,665 US patents. 9,874 international patents. He actually holds the world record on the as the most prolific inventor alive today. If you look him up, so who's got the most patents? Thomas Edison, something like 600 and something, which is amazing as well, by the way. But nobody knows him because he's not a disruptor. Most of his patents are in the areas of printing technologies. So a lot of the 3D printers that we use involve his patents. Sound technologies. A lot of the sound systems that we use involve his patents. So he's a technical inventor. All of these things in front of him are things that he has involved. That's his lab and his patents and stuff like that. So he's a very successful person, but we don't know it. So it's not necessarily, you can be successful without having to be famous, and well, possibly vice versa, I suppose, depending how you spend your money. Yeah, worthwhile mentioning that there's room for lots of different types of people in this environment as well. And I suspect, he'd be the sort of person that would be behind somebody like Steve Jobs, helping him to provide, to supply the technology, which then people like he can then promote. I think we also know about James Dyson, yeah? This figure, however, so this is another number which is worthwhile bearing in mind. Before he got, he's famous for this vortex-based generator for vacuum cleaners, yes? So the bagless vacuum cleaner. The fact that it's a very efficient way to create a vacuum. It doesn't degrade in vacuum suction power over time because it doesn't clog up as easily and things like that. Before he got to a working prototype that he felt worthy of presenting for production, he went through 5,127 prototypes. So he's cataloged. So I always present this to my students when they're doing their final year projects. Because I say, look, don't divide your time up by beginning and end. Okay? Divide your time up into segments where you want to achieve a particular goal, and then continue by doing that in an iterative way. Most students, when they think about their project, they think, okay, this is the problem, this is what I need to provide, I've got 10 weeks to do it, that's my project. Okay? When what we do and what we're looking at, and particularly now that I'm in a design and production and management department, is I get my students to think in segments. And you should think the same way. Whether you're a researcher, whether you're thinking about setting up your own businesses, even if you're an educator. I hate now education systems where you basically say, what do I need to teach in order to fill up 10 weeks? Because that's what most courses are. Yeah? You have a 10-week or a 12-week or whatever semester, and you're supposed to teach fluid dynamics, and therefore you continue to teach fluid dynamics until the time is up. Nowadays, what you should be doing is thinking, what does my student need to know? How much fluid dynamics does that student need to know in order to solve the problems that we are currently working on? So now, myself and my colleagues, we break up our course material in that way. And if it only requires 2 lectures, then only deliver 2 lectures. Now, bear in mind, this is coming from a person that has been told that he has to present 10 lectures on a subject of medical prototyping. Okay? So I realize that there are artificial situations and artificial conditions in everything we do. But the important thing nowadays is that we want to teach our students and make sure that they are ready for employment, what we would call work ready. And if you want that to happen, then you only teach the amount of fluid mechanics or fluid dynamics that you think they'll need to know in order to get a job. And that might be different for one student to the other. So what we should now be going back to is the old days. You know, Oxford and Cambridge universities, they still teach that way. There's very few lectures in Oxford and Cambridge. It's nearly all tutorials. Your students go in little groups to the professor, and you talk around a subject, and you work out what it is that you need to know. You guide them through the learning processes. And because you've got very, very clever students, because they're paying lots of money for their tuition fees, it can be enabled that way. But we should all be doing that, to be honest. Anyway, I am, as usual, moving off topic. Okay, so I've got a few images now where I want to just sort of enthuse people or encourage people to be thinking creatively and innovatively. So fashion industry is now starting to use additive manufacturing in a variety of ways. A lot of them, in my view, quite questionable. They're very visually, the impact is fantastic. I prefer clothes which are comfortable, and I haven't really come across many examples where 3D printing helps with that yet. I mentioned about things like gaming figures and the fact that whether we like it or not, a lot of people spend a lot of time and a lot of money on playing games. And so this is part of our society culture. You call it what you will. I suppose it's always happened. The thing now is that, yeah, you should be considering the possibility of making businesses out of it. Musical instruments. It's becoming more and more common these days to use 3D printing. It's a great sort of combination, if you like, combinatorial technology where you're combining innovation, creativity with functionality. Yeah. I mentioned about the fingerprints thing. I mentioned there was a video about how you produce these fingerprints. So your 3D printed model starts off as the game model. Think about what I mentioned about gaming when I talked about scanning technology. You can fool people when they're playing a game that something is more three-dimensional than it actually is by using bitmap ray tracing techniques, rendering methods. That doesn't work when you're actual 3D printing, so there's actually a lot of post-processing of the game data before you can actually make the part. For example, if the character is wearing a cloak, you know, a cape, that cape in the game is a zero thickness surface. And if you print that, nothing there. So you have to post-process the game data to apply thickness to the components. Some of the features might be very fragile. So this is the powder binding method. So you've got a printer head gluing powder particles together, and now you can see the part being uncovered by the loose powder. So using an air jet to just blow off most of the powder. So it doesn't look very impressive at the moment because it looks all kind of dirty and still got lots of powder attached to it. So there's additional touch-up that needs to be done with maybe a more precise air jet, just cleaning off all of the finer details. Still doesn't look fantastic because you essentially got the color is kind of embedded in the powder itself a little bit. So this is an infiltration process. I mentioned that the parts are quite weak, so that you have to soak these parts in a resin. So that's them being dipped into a resin bath. And the resin basically has two purposes. It strengthens the part. See the parts coming up now. And it also enhances the coloration because it kind of stops the reflectivity or makes them more light absorbing. So now the parts look pretty good. You need to just bake them so that they're nice and tasty. And now you can see the colorations, and I mean, this is a few years ago. This video, they're getting better and better, and the color quality is improving. And in fact, now I mentioned about the object Strada machine, which produces color parts. The coloration on their parts is even better. However, I think the cost would be prohibitive. So this is kind of like cost effective. The parts themselves, the model so big that you're seeing here, are about this sort of size, around about $100 US. So expensive, but not hugely expensive. In particular if you're a fanatic, I suppose. It says made in Germany. I didn't think they're made in Germany. So pretty cool. Some ideas about, well, they're not really new business ventures anymore. In fact, for new business ventures, you should look to companies like Shapeways to find out who's using them as their shop floor. And there's a few other portals for setting up businesses now. As a matter of fact, there's a lot, I guess. What would be a common one in India for doing this kind of thing? Is there an Indian version of Shapeways? No? So there's no entrepreneurial Indians making stuff on their 3D printers and selling them over the internet? Yeah? But it's not a popular process. Okay. Okay. So they make their own websites, essentially. Yeah. So nowadays, particularly in Europe, the US, China is really big on this as well. I mean, Amazon, people now set up their shop entirely within Amazon or eBay. Alibaba in China. So all of this kind of thing, Shapeways is slightly different from this because it specifically deals with additive, but there's a lot of potential there. I mentioned about Scott Summit and his work. This is a different example. So there's a number of competitors. As soon as you get a great idea, everybody copies it, isn't it? So sometimes they say the early bird gets the worm, so they become the leaders. Sometimes they say the second mouse gets the cheese. Yeah? So there's nothing wrong with copying it, providing you can also add value, or you can also personalize. So nobody should copy identically, but there's nothing wrong with adopting a similar business model if it looks as if it's going to work for you and for your product. So good examples there. What else have I got? Oh, sorry, back. No. Going back. Back. Stop. Go back to food printing. Right. Okay. Because of videos, you see. So a few people have already mentioned about food printing. There's quite a number of printers kind of like this sort of thing, the chocolate printers. I even saw just, do you get Cadbury's in India? Yeah? So Cadbury's just a couple of days ago launched their, because I think they're 100 years old or something, or 150 years old, yeah, or something like that, and they launched a chocolate printer as part of their birthday celebrations, I think. So confectionery printing I kind of like and kind of understand, because often you can associate confectionery to customization. You know, if it's somebody's birthday and you want to do something spectacular, present it to somebody, you don't do a personalized curry, I don't think. You might do a birthday cake, however, yeah? So obviously you still need to feed them curry, but that's not the purpose behind the 3D printing. That's where I think there's a bit of confusion. You know, the idea of having you know, something like a curry and 3D printing that doesn't make sense to me, but some people seem to think that that's a good idea. There is a cooking technique called molecular gastronomy. Have anybody heard of that? No? Yes? Okay. So in that, what you do, it's kind of like this kind of thing, where you provide, you actually work on usually very small items, and sometimes you make them so that they look like they taste like one way, but they actually taste completely different. You know, it looks like a candy, but it tastes like a curry, and you know, or vice versa, or they have very, very specific flavors and things like that, and it's like a chemistry process. It really is. They use you know, liquid nitrogen and use hydrogel techniques. So there's a lot of molecular gastronomy that's kind of like what some of you guys are thinking about from tissue engineering. And so there are people playing around with that. The first example, that's kind of like this thing here. Is my mind actually, I think this is just growing food, but I you know, the first one I came across was a restaurant in America that was playing around with 3D printing, and they produced a shrimp paste, which was very tasty and very, you know, it's all very organic and uses the best ingredients and things like that. But then they used a printer to make them into shapes, and so they had a 3D printed shrimp paste model of the space shuttle, and they used to, put those on a plate and with a little moon on it and stuff like that, and yeah, stuff like that. So I can see that 3D printing will go into the culinary industry. You may even find that you can buy 3D printers for your own home that are based around food, but there's just recently a 3D printing pasta maker. Kind of think that you do this 2 or 3 times and everything, wow, and then 4 or 5 times you think, oh, well, it's a bit too much trouble and I'm bored with it and I want to do something else. Yeah, so that's kind of how I feel about food printing. There's a very good friend of mine actually is in America who, his name is Jaana Kaitanen, and he's famous for doing a lot of lighting products and stuff, and his more recent venture is to make 3D printed ice pops. And he basically, his business model is he does it for conventions. Like, we could have a GIAN ice pop, and he'd make them for you using a 3D printed ice pop mold. That'd be pretty cool, wouldn't it? Let's go have a tea, and you should have thought of this, Ravi. You should have thought of this. You should have thought about, we have tea time, and we go out there, and we've got a 3D printed samosa or something like that, huh? Okay. I mentioned about innovation. There's a lot of innovation that's going on with 3D printing. That's kind of where the business side of things is playing around and experimenting. And again, it's because of cost. We've got machines which we can play around and build all sorts of exciting products and things like that and ideas without having to spend too much money on it. And so if we then think, this is a great idea, millions of people will want it, you can turn it into a business, scale it up, again, without too much cost. So investment cost as well. I mentioned about the Strada. This is another video. So this is proof that this car actually exists and works.
Local Motors recently created a 3D printed car called Strada.
A car exactly how you want it and built while you wait.
The vehicle was made during the 6-day-long International Manufacturing Technology Show in Chicago. Local Motors partnered with Cincinnati Incorporated, the Oak Ridge National Laboratory, and the Association for Manufacturing Technology to make the car a reality. The Strada is a 2-seat electric auto that has a top speed of 40 miles per hour and a range of up to 120 miles. Staffers at Scientific American say the vehicle was built in about 45 hours. Less than 50 parts were used in the final product. Items including the battery, motor, and glass windows were added after. The Strada project isn't just an experiment. Local Motors hopes to market the vehicle sometime this year for a price of up to $30,000. CEO John Rogers remarked, "We expect in the next couple of months printing a complete car to be below 24 hours and then eventually get it below 10 hours, down from 45 hours currently."
Interesting. Oops. I'll skip that one. So again, so the good example. So we've discussed this already yesterday, I think it was, and yeah, so just to prove that it does exist. Another one which is sort of more innovation sort of thing, industrial design. There's a lot of designers playing around. There's any number now of customized in-the-ear earphones, which when there's kind of like one where you take your phone, and you take a picture of your ear, and then you send that off, and then they design this so that it fits in the ear and the earplug doesn't fall out, that kind of thing. any number of different now designs of artificial limbs. People playing a lot with lighting products. Yeah, some really nice stuff. My wife wants one of these. I've looked at the price, so she's not getting one. And you know, all sorts of things that are either completely built using additive manufacturing or definitely prototyped quickly and easily, and maybe even also the tooling developed around it. This one, I don't know if you're familiar with some of the work at MIT by Neri Osman. So this is glass printing. It's pretty cool. Yeah, there are obviously some limitations to this. As you can see, it's not totally transparent, so it's not really about providing functional glass lens type technology, but more playing around with optical effects and more for the purposes of visual. But again, proof that it can be done. And if you've got some ideas and you've got a bit of, you've got a really expensive lab and great funding, this is what you can do. Let's skip all that. I don't really want to be doing stuff on business really. This one, yeah, even this is not really. $8.4 billion market. I think it's already getting there. I don't think it's not going to be 2025. It's going to be twice that by 2025, I think. You know, we're really talking about extremely. This one, I don't know if you've seen this video before. Anybody? No? Just a little bit of fun.
You ready, Bobo? DJ Bobes? Yeah, hit that track. Holy moly, MIT done did it. Got machines printing out honey, but actually it isn't. They got gooey molasses coming out in labs back to back in the track. Voila, it's glass. I'm like, wow. They gotta know to mold some old crazy shit. Made a printer last week that can print like 10. The multi-fab printer that can print like Prince Purple Rain and things. Man, the game to change what you expect from brains that can connect like trains. I say go. Now down in Chattanooga, got two dudes that say they do's it, printing super strong structures that nobody can fool with. Park a truck up on that bitch and it ain't moving. Ask them to print me a house, they said let's do it. We thinking big boy-ish, that's why we quit our shifts to 3D print your crib. I said, yo, on another note, Google's dropping nose with their venture capital. Carbon clip is the shit and it goes real quick, so they dropped 100 mil like it ain't no dip. Also made a phone that they call Tango, so every bro on the globe can 3D scan they chode. Wound up, cause it's coming from the ground, bro. We go plastic made from a cup of joe. Really though, it's grinds that they mash up, then they wrap it up in plastic and they ship it to your home. Oh no, my phone don't quit, but if I had a nipper, man, I could fix that with a tiny 3D print that you hold like this. Find 2 batteries and you're back up quick. Printer of the week, printer of the week. Printer of the week is a geek like me. I said printer of the week, printer of the week. Printer of the week is a geek like me. I said yo, printer of the week, printer of the week is a freak like me. I said yo, printer of the week, printer of the week is a geek like me. Goes out to Josh, a German engineer making the booty big old bike bubble machine. You can find it, there's designs on Thingiverse. Make your own bicycle bubble machine. Yeah, all the links can be found below if you want to read some more. Special guest, DJ Bobes. Beats, Otis McDonald.
Okay. It's quite good for a Friday morning, isn't it? Yeah, we are. All right. So what do we got? What are we doing there? Is this your exam, or is this just a QA? Just a feedback session? Oh, it's a great time to do the feedback session. Thank you. On jewelry? Yeah, loads. There's a lot. I know. I know. You told me that Rutesh has got some problems, is he? Yeah. Okay. So my ring was done by a guy called Rutesh Shah, who runs a company, or did run. Is it still in existence, the company? Yeah, called Innovarium. So he used kind of like a conventional mixture of 3D printing and casting for conventional jewelry production. But there are now quite a lot of gold printers available. There's at least 3 manufacturers that allow you or have the capability for printing gold. One of the most famous ones is actually in the UK, a company called Cooks and Gold, and it's based around the University of Wolverhampton in near Birmingham, and they've been running for quite a long time. And in fact, I got another ring done for my wife, which was printed in gold. So this one wasn't printed in gold, but it is possible. In South Africa, Central University of Technology, they're looking at platinum printing. It was interesting. They started work on this a couple of years ago, and I was talking to the researcher there, and he was telling me that when they first, so the sponsor is actually a mine in South Africa, and in order to deliver the platinum, they delivered about 3 kilos of platinum powder. Yeah, they shut down the university on a Sunday, so they made sure there was nobody else in the university. They had armed guards around the university. They then flew in a helicopter with the platinum. They then had an armed guard to take from the helicopter to the lab for them to do the processing. So they then did their experiments and things like that. And they had to account for every gram of material. So they had to deliver it all back eventually. So they did the same thing back, and then they took it all back, and then the mine then weighed how much, so all the powder and all the things that they'd made from it, to make sure that it hadn't found its way into anybody's wallet or...
But in handling system of the printer, there will be here and there something after the screws, like it will fix the powder at least.
Yes, absolutely. So they had to account for that, essentially. So that, if they lose maybe 50 grams, then might be okay, I suppose, but they would have to sort of explain why they've lost that amount of material. But
not to what the printer they use, but it will be definitely 10 times the cost of the 1/10 of the cost of the material into the respective.
yeah, they used a EOS DMLS system. So yeah. So you're right. So there is, and there's also a company in Switzerland, also quite commonly doing printing in jewelry. There's a lot of jewelry designs. There's not so many jewelry makers, but there are a few. Another good friend of mine, his name is Lionel Dean. He's a British designer. He's been working in this space for 20 years or more, making and designing jewelry as well as other stuff. But yeah, he's got a few examples. He's the one that actually designed my wife's ring as well. Yeah, yeah. So the majority of the systems will be powder bed unless they're using a casting system as well. I mean, if you can imagine, I mean, obviously, a lot of dental work is also uses gold as well. So micro casting, precision casting of gold is a well-known and well understood process. So it's not like that is a problem space. I suppose the problem space is really about the materials handling and some of the processing if you're doing powder-based sintering. So yeah, you're right. Any other questions? Yeah. 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 Yeah.
And what about the wasting? What about the joining? Because we are using
Yeah.
some here we are using some kind of forex kind of thing.
Yeah. Yeah. That starts to come into the specific technological solutions. So there are always ways to do finishing. Even in a normal jewelry manufacturing facility, if you are doing lapping or burnishing but they still try to recover the materials, yes, even afterwards. So a lot of it is about the precious material, and you want to be able to recover it. So they've experimented, and Cookson have experimented with a whole variety of different, some of the sort of more conventional ways of finishing, like sort of hand finishing, but then some automated finishing methods like barrel finishing, those kinds of things. They all kind of work. I mean, one of the reasons why gold is chosen as a material is because it's quite easy to work with. It's a soft material, and therefore quite easy to come up with a nice finish, and you can play around with the finish very easily. Yeah. 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 So a wire-based printer, I'm not aware of one. Yeah. Yes, it wants a FDM style. Yeah. Yeah. That's a pretty good idea, actually. I mean, if you see the glass printer, I mean, those temperatures are way, way higher. So it's not a matter of the temperature, and gold, I don't know what the melting point of gold is. What is it, about a few hundred, maybe 600, something like that? It's below 1,000, I think, yeah. So it's one of the lowest melting point elements, isn't it? You can melt gold with a butane, can't you? Yeah. So that's not a bad idea. Okay. Yeah. Yeah. Uh-huh.
So actually, before surgeries, doctor can do the virtual planning. So after the surgery, also they can compare with the.
Yep. Yep. I can put that presentation up now because I haven't finished that one, had I? Are we on a break now, or 10 minutes? 10?